Okay, now we'll talk about radiation pressure. Okay, now let's say you guys have, you guys all know this. Let's say you shoot a gun at a target. Okay, now when the bullet hits the target, it transfers momentum to the target. Similarly, if you shoot a beam of light at something, the photons impinging or being absorbed by the target, you transfer momentum to the target. So photons carry momentum. Okay, so if a beam of light, if this much energy from a beam of light got absorbed, this much momentum is transferred to the object. So the momentum transferred is the energy absorbed divided by the speed of light. Okay. Now here's how you remember this. Okay, so just classically, so look at the kinetic energy. 1/2 mv squared is the kinetic energy, and momentum is mv. So kinetic energy divided by velocity would be 1/2 mv. Okay, this would be momentum. So energy divided by speed should have units of momentum. Okay, and that's what. So in a beam of light, when you absorb this much energy, this much momentum has been transferred to you. The energy absorbed by the speed of light. So if the surface is a perfect reflector, this is for absorption. If the surface reflects light, so here's this surface reflects light, the black surface absorbs light. Okay, so if it's a perfect reflector, then the momentum transferred to that object is twice as much. Okay. Now we'll come to this fact a little later, but so if it's a reflector, twice as much momentum is transferred to it. Okay. So now let's talk about radiation pressure. Pressure is force. So what we're doing is okay. So here's a beam of light falling on this surface. Okay. So a beam of light can be thought of a bunch of photons, and capital P is pressure. Okay, so that's what we are interested in. What kind of pressure does this beam of light exert on this surface? All right, so pressure is force divided by area. Here's the 1/, area. Force is rate of change of momentum. Okay, force is the rate at which momentum is transferred. You saw that momentum was U by C, and this is the energy absorbed. So du by dt by A, and there's area is the area vector. Okay, let's we'll derive that for you guys. Oops. Pressure is force over area, and force, according to Newton's law, is rate at which momentum is transferred. Momentum is energy absorbed divided by C. Okay, so 1/A d by dt of U by C. Oops. Okay. And so 1/C d by dt. Okay. And this is intensity, this term. So that's 1/C divided by intensity. Okay. And so the pressure exerted on a beam is the intensity, the pointing vector divided by C. Okay, that's if the beam is absorbed. And if the beam is reflected, then the pressure is twice as much. Okay, so for a surface that's absorbing, so this is for an absorbing surface. For a reflecting surface, the pressure is twice the pointing vector divided by C, or twice intensity by C. So a beam of light can exert a pressure on a surface, and the pressure exerted on the surface depends on the property of the surface. If it's an absorbing surface, then the pressure is 1/2 of that of a reflecting surface. Okay. All right, well, is this all theory or do we have proof? So here's proof. Okay, so here's a comet. A comet, as you know, is a ball of ice and dust, dirt. And when a comet comes close to the sun, some of the material of the comet evaporates, and it has the evaporated material has ionized gas and dust, neutral particles. Okay, so let's see. And that's what we wanted. Okay. So here is the sun. So here is the sun. And the sun is emitting photons, and there are charged particles also escaping the sun. These charged particles are called the solar wind. And this is, of course, radiation. Okay, so here is the comet, and stuff is evaporated. Okay. And this thing has dust, which is neutral particles. And this is just terminology. Gas, which is ionized gas. Okay, so there are charged particles. And of course, the solar wind repels this guy, and the radiation repels this guy, exerts a pressure on the neutral dust particles. And so you see two tails. So the gas tail is the ionized gas being repelled by solar wind, and the dust tail is the tail that's repelled by the radiation pressure. Okay, and this is always radially outward from the sun because of the magnetic fields and stuff like that. The solar wind gets redirected, and so this is not pointing at the sun, but this guy is always pointing at the sun. So the neutral dust tail is being pushed by the radiation pressure. Okay, so, and we've also demonstrated this radiation pressure by using flying solar sails. And the idea is so sunlight bouncing off this will push this solar sail away from the sun. Okay, so when light photons reflect off these sails, these transfer momentum to the spacecraft. Okay, and you can go to the Wikipedia page and look at the solar sails page. Okay. So solar sails are a method of spacecraft propulsion using radiation pressure exerted by sunlight on large mirrors. Based on the physics, a number of spaceflight missions to test solar propulsion and navigation have been proposed since the 1980s. Yeah. Japan has actually flown one. I'm sure the US has flown one too. But anyway, you guys can. So the total force exerted on an 800 meter by 800 meter solar sail, for example, is about 5 newtons. Okay, so 800 by 800 newtons solar sail. 800 is, so imagine a 10 football field by 10 football field size solar cell. The force on that is 1 pound. Okay, so it had better be pretty light to get pushed around. Okay, so that's the kind of pressure you feel. All right. All right, so let me pause again.